In this video, we are going to learn about backtracking and why backtracking occurs when we traverse through trees. And we're also going to debunk some misconceptions about backtracking. All right, so this does require that you have done 27.04 file system part 3, because it's going to go over the answers for that. All right, so quick warning. All right, so I'm going to scroll down here, and there is the answer for this problem. So that's all the data definitions and stubs and etc. I'm going to grab one of these diagrams and stick it up here to the right, because we need to look at it. So, one moment. So hopefully you guys, oh, it's too zoomed in. Hopefully you guys can see the diagram over here. All right. So let's just go down to the code here. It's already been done for us. And let's explore what this code is doing, right? So I'm gonna grab my pen out 1 second. So there we go. So this searches the current directory, right? So this search cur files, right? So let's say I'm looking, given this entire documents tree, right? I'm looking for to do, right? That's right under me. That's my files, right? So to.txt, it will produce the number 10, right? That's what this find-filesize directory does, right? So if it is my current file, right? It's right under me, then, right? If it is my current file, then just produce the file size. So we would get 10 back. But if it isn't, then this branch would find all the files in the subdirectories, right? So if I were looking for part 3 instead of to do, which is right under me, well, I would have to traverse my subdirectories, right? So documents has 2 subdirectories, scripts and life. So it's going to go to scripts first, check all its 3 files. So 1, 2, 3, right? Check all its files until it finds part 3. And then we see the size over here. So it's going to produce 17. So that's this test over here, right? That's producing 17. All right. Going to clear the screen. So that's all well and good, right? This one searches the current file, current directory, and otherwise this one searches the subdirectories, right? So searching the subdirectories is a little more kind of weird, right? Let's say we're looking for a cover.pdf, right? Given this entire documents tree, right? This entire documents tree. All right. What it's going to do is it's going to check the current directory. So search cur files, right? To do.txt as not cover.pdf. So I'm going to check my subdirectories, which is starting from scripts first. I'm going to check, is there a cover.pdf in this scripts folder, right? And we see that 1, 2, 3, 4. None of you guys are cover.pdf, so we're not here. And this is a case where it's all files, so that's fine. If there were subdirectories in scripts, like if scripts had another folder, it would go down and traverse that folder. But in this case, scripts doesn't. So it's going to backtrack up to documents and continue to life, right? So we just went from documents to scripts. We checked all the things in scripts, and then it's not here. So we go back up and then go to the other subdirectory in documents. So now we're at life, and life has no files, right under it. And it only has subdirectories. So going to the subdirectories, we go to the left one, and we see work. So work is a subdirectory, so we got to go through that again, right? And this again is mutual recursion. This is going to call us back, so that's going to allow us to traverse arbitrarily deep. All right, so we check every file in here. We find work resume.pdf. In work, it's not you, and it does have a cover. So there we go. We return to, and that is our answer, right? So that this backtracking nature of going from documents to scripts, back up to documents, to life, to work, and then finally getting cover is what we're trying to explain over here, right? Let's say we're looking for, let's say school had another file, right? School had a hello.txt, and we want to search this given this entire file tree, right? Well, again, it's going to go to documents, check all its files. It's not you. You're not hello.txt, right? To do is not hello.txt. We go left to scripts. We check all the files in scripts and subdirectories. In this case, it doesn't have any. So it's not here in scripts either. So I'm going to go back up to documents. I'm going to go to life, and then life has 2 subdirectories. I'm going to go to work. I'm going to check works files. Let's see. You're not hello.txt. You're not hello.txt. I don't have any subdirectories either. So I'm going to go back up to life, and then down to school, and then from school, I will find hello.txt, right? So again, this backtrack nature of going to documents, checking its files under it, and then going back up and then going to scripts. It's not in scripts. Go back up to continue off from documents, and then go to life, and then go to work, and then find out that it's not in work. Go back up to life, and then go to school, and then finally find it, right? This backtracking nature is what we're trying to explain in this video. All right, so why does it backtrack like this? You might be wondering. Well, it turns out the reason why it backtracks is because those are the rules for function execution, all right? So notice how nowhere in this code do we actually write explicitly, if you can't find it, backtrack, right? Like this, right? We don't explicitly write the backtracking part. Again, if we were looking for cover in this entire documents tree, we go to covers, to documents is current files, not here. Go to scripts, it's not here. And then scripts would backtrack to documents, right? We don't explicitly write the backtracking part in code. That just happens to be how the function executes. We do write the explicit search, right? The searching over here, which compares the files, file name and the file name that we're trying to find, right down there. But we don't explicitly write the backtracking code. The backtracking nature of this traversing through trees is sort of implicit, right? And we're going to review why is that the case. Well, it turns out that it's kind of always been the case, right? So let me just undo this. And we'll open up a new tab here and we'll paste some code here. All right. So you're familiar with this math expression, and multiplication is waiting. All right. Waiting. All right. So if we evaluate this step by step, all right, this multiplication is called first, but it can't execute, right? It's executed last. So there's a difference between calling and executing a function, all right? So we go from left to right and we see a plus. Plus, again, let's see all its operands at the values before I can execute, right? It's called second, but it can't execute yet until all its arguments are values. So we keep going and we see 3 is a value, 2 is a value, and then we encounter a division of 5 and 5, right? So that is going to be called and then executed, right? So this is called third and executed first because this division actually runs first. So this turns into a 1, and notice that we backtrack and we can finally do this addition because this 5 divided by 5 turned into a 1, right? So again, this was called second and this was called first. All right, so after we're finished with this division, we can backtrack to this addition and finally do this addition, which will produce the number 6, all right? Now we're gonna go to the next operand because, again, multiplication is still waiting, and we can backtrack to it later after we evaluate all the arguments to values, right? So minus 4, 2, this is gonna become 2, and then we can backtrack and finally do this multiplication, which is going to be executed last, and this is gonna be 6 times 2, which is gonna be 12, right? So if I run this code, it should produce 12, right? So yeah, it turns out that function's kind of already backtracked if you were paying attention. So there we go. There we see the 12. All right. So this happens mechanically because programming languages come with what is called a stack. All right. So I'm gonna move this to another monitor, and here is the stack. All right. So you can physically imagine like a stack of plates. You would never remove a plate from the middle. You would always remove a plate from the top because you don't want to break anything, right? And you always put a plate on the top, right? So this is the initial call, and every time we encounter a function, we push what is called a stack frame onto the top of the stack. And the stack keeps track of what function is currently running, the variables called with a function, and the pending functions called but are waiting to be executed, right? So the function way at the bottom of the stack is the pending functions that are called but are waiting to be executed. Again, calling and executing are two different things, all right? Because calling implies that you may have to wait until you get to execute, right? So if we go from left to right, we want to do multiplication, but all your operands are not values yet. So you have to do this addition. We encounter the addition function. So you push that onto the top of the stack, creating a stack frame, all right? And then this is going to be the thing that is the currently running execution. Right, so anything on top of the stack is the current running function, right? And we evaluate this, we try to at least, and we see plus 3, 2, and then a division by 5, right? We encounter another function call. So you push division onto the stack, and we end up over here, and we end up with division by 5, 5. So this is going to be the current executing function, right? Anything on top of the stack, way on top, is going to be the function that's currently executing. All right, I'm gonna scroll down here. We resolve the division to be 1, and then after that's done, we unwind the stack and put this in this one position, all right? And we keep going down. We can see 3 plus 2 plus 1 is going to be 6. So we resolve that addition, and then that bubbles back down to this spot over here, 6. All right, we encounter a minus 4, 2. So we push that subtraction on top of the stack, and then that executes, and then we have to resolve that subtraction. That becomes a 2, and then that 2 gets placed here, and then 6 times 2 is finally 12. All right, so this is the animated GIF version of it. I recommend you go to this website and try to find it. But let's just wait for this to loop actually. So shortly, there we go. All right, so here you can see the plus being pushed up, and then the division being pushed up, and then division revolving, and then being put back down in its place, and then like so. All right, so 2, and then that becomes 12, right? It gets, the unwinding part is kind of done in one step to save time, but this is the mental model, right? The stack grows up and then shrinks down, right? And in reality though, what happens is that pushing things onto the stack creates a stack frame, and that actually comes with a computational performance cost, right? So if you have too many, your program is going to slow down, not to mention it could actually crash with what is called a stack overflow. So what Racket does with these simple operations like multiplication and division and subtraction, these don't really create a stack frame. Racket has a way of optimizing them so they don't create a stack frame, but right now we imagine that they do because it's a good mental model and it fits. It's a good mental model to explain what's going on and why a stack works the way it does. All right. So it turns out that you can actually visualize the stack for yourself. So we're going to go to Racket and we're going to go to our program over here. I'm going to remove that and I'm going to scroll up here. So what you have to do is you have to change the language level from ISL to ASL, because that's going to give us the debugger that shows us the stack. All right. So ASL, and then you're going to hit debug and you're going to pick a debug spot. So let's just debug the one looking for cover. Hit pause, and if you hit debug again, or you might have to hit go sometimes, it's kind of weird, but once you see this green arrow, you should be good to go, and then you can actually see the stack here in action, right? So if I step over it, right, it grows and it shrinks, right? Grows and shrinks. All right, and you can actually see the variables here, like so. There's something a little bit buggy about the ASL debugger, right? These question marks over here, I think that's a bug, and I will probably have to ask the Racket developers to fix it. So we would need to change the full Racket language to see the stack in action, right? Because those question marks, I don't know why they're there, and it makes a bad job at illustrating the stack, right? So let's change to the full Racket language, and there will be adjustments that you have to do to your code. So here's the full Racket language. You have to make sure #lang Racket is on top, and to make sure that you have to comment out some things, right? So checked signatures, right? Anything that has checked signatures, you have to comment them out. Templates, you have to comment them out. Racket doesn't really have a notion of these dots, so we have to comment them out. So signatures, templates, we have to comment them all out. And in a way, they should be commented out in the first place. You want to do the renaming. All right, let's see what else needs to be fixed. Check expects, right? Racket doesn't come built in with check expects. ASL, BSL, and ISL, the teaching languages do, but the Racket language, you have to import it as a dependency. So it's going to be require test engine / Racket tests. Right, so that will at least get the check expects to stop yelling at us. All right, so the check expects aren't actually going to be ran. We're going to call it manually to debug. Right, so I'm going to copy and paste one run over here. All right, we run this code. Oh, let's see, we get an error. Search curve files undefined, cannot reference an identifier before its definition. So this kind of indicates Racket has, the full Racket language has some different rules as to where functions can be placed, right? Since search curve files, we're calling that, right? It has to exist before we call it. So we have to move this entire code block down. So again, you do have to make some adjustments to your code if you want to use the debugger over here, the full debugger. All right, so this works. And what we're going to do is we're going to hit the debugger over here, and we're going to hit pause at this point. Hit go. We're trying to get the green arrow over here, so we might have to hit debug again. And there we go. All right. So you can step through this code like you would normally, and then you see the stack over here. There are no question marks this time. You can view the variables of the current variables, right? With the state of what they are. So this is the entire documents directory, as you can see. And if we hit step, right, no question marks, and we can see the stack grow and shrink like so. Right, so it's going to grow and shrink, aka it's in a way you're going to see the backtracking nature if you write down all the variables over here. Right, you can see it backtracking and why it backtracks in action. Again, right, nowhere in this code do we actually write, if backtrack, right? If you can't find it, backtrack. You do the if search, right? If it exists, then get the file size. Otherwise, search the current files or search the subdirectories, right? We write that part, but the backtracking part, again, is implicit. It's just how the code runs, because that's how functions behave over trees. All right. So in this video, you learned how and why functions backtrack, the function stack model of execution, right? You can find it on this website here. And that backtracking implicitly happens, right? In that we don't explicitly write code that backtracks. It just so happens that that is how the code executes, right? That's how we backtrack in general, all right? Anywho, that is about it for this video, and I'll catch you in the next one.